All right, so for the last question for this module, the last example for this module, last time we had a discharging capacitor. Now we're going to charge one up. So last time we had a capacitor sort of like this, and it was going to discharge through a 100 kilo ohm resistor. This is going to be 100 nanofarads now. I think after I just said that's not what we use, but that's okay. And then I'm going to charge it up with a 9-volt battery because 9 is such a wonderful number. And so this is going to charge up this capacitor like this. So let's say this is the max, QM, right? And this is the charge as a function of time. It's going to go like that. It's never going to quite get there. So what we're going to do is we're going to look at getting to the 90% mark. So this is 0.9 QM. And that's the time that we want to find there, this time where it gets to 90% of the maximum. So technically it doesn't ever get there. In reality, there will be fluctuations, and fluctuations will actually make it hit that maximum level. So let's see what actually happens. Well, we have this as our charging equation. Like I said, this is an exponential. It's just an exponential increase. So we'll call that QM. We'll call it QM because PowerPoint wouldn't let me type max because it thought max was a function. And then we have 1 minus e to the minus t over rc. So again, we're looking for something in that exponential, which means we're going to have to take the logarithm. So eventually we're going to do qt over qm, so e is all by itself, right? So we want qt over qm actually minus 1, right? And that's going to be equal to e to the minus t over rc. So since it's going to be equal to 1 over all that t to the minus rc stuff, what we're going to have to do is we're going to have to this is bad, actually. What we're going to have to do is we're going to have to go through and do all the math to get there. So first, let's just find RC. We couldn't really do that previously because some issues with something else. We could have done T over R, but that doesn't feel so good. So let's just find RC. Right, RC was 100 times 10 to the minus 9 farads times 100 times 10 to the third ohms. So that's going to be 10,000 times 10 to the minus 6 seconds. Is that right? So that's going to be 10 milliseconds. Okay, so that is our time constant. Let's see what we can do with the rest of this. All right, so we can take that in here and we can put it in for RC. QT over QM, that was 90%. So we've got 0.9. 90% is equal to 0.9. And so we have 1 minus. So what we're going to have is sigma, e to the minus t over rc, which is 10 milliseconds, is equal to 1 minus 0.9, which is 0.1. And you remember last time I got a little bored, and I said, well, I didn't get bored, but I decided that I didn't want this 0.1 thing in there. What I wanted to do was flip it over. So I got rid of the minus sign in the e before I took the logarithm, so it was e over t to the 10 milliseconds. and 1 over 0.1 is 10. So when I take my logarithms, I end up with what? I end up with t over 10 milliseconds is equal to ln of 10, right? And ln of 10 is equal to 2.302. So that means the time it takes to discharge is going to be 23.02 milliseconds. Who cares about the 0.02? I don't think you can measure 0.02. Well, I mean, you can if you have a trigger. If you can with electronics. You can't with your stopwatch. All right, so that is that. Oops. Come on. Okay, so 23.02. And it's more or less a straightforward way to get down there. All right, so again, the tricky part is playing with logarithms. Again, you need to isolate E before you can do anything with the logarithm. After you isolate E, the world is your oyster. Okay, so that's probably sufficient for now. And I will do the homework examples, and then we'll talk about the test, and then we'll go on to magnetism. Magnetism, that'll be fun. All right, bye now.